Lecture 3. We start this lecture by revisiting the law of conservation of mass, just to remind you of it. We're going to talk about a number of laws in this lecture and a little bit of historical aspects of chemistry. So, as you may remember, for a given reaction, you start with a certain amount of reactants, and the mass of products that you generate, ultimately, you find out that collectively the mass of the products equals the mass of the reactants. And it doesn't matter if you increase the amounts, decrease the amounts, or make it super large, make it a lot bigger, make it a lot smaller. The point is that if you add up the total mass of the products with the total mass of the reactants, you have the same mass on both sides of the equation. And this is the main premise of the conservation of mass, that you can neither create mass nor can you destroy it. Now, when you learn about nuclear chemistry, something that will take place in a different chemistry class, um, you'll find out that this isn't exactly true, but within the context of what we typically do in an intro chemistry class, the idea that mass will not be changing, the idea that it will not be created or destroyed, is actually fairly accurate. All right, now, there's other laws that also have some historical connotations. These are the laws of definite and multiple proportions. And this is what was observed prior to the periodic table becoming a thing. So this is when scientists were beginning to look at the amounts of elements present in a compound based on mass. And based on mass and mass only, they were able to determine what was happening. Now, the law of definite proportions basically tells you that for a compound that contains some elements in it, the ratio of the masses of the elements will remain constant. Like you could have more compound and therefore you have more mass of elements, but the ratio will remain the same as if you had a smaller amount of compound and a smaller amount of elements by default. So for instance, if you look at iron 2 chloride, or iron that has two chlorides present in it, we could start with a mass of 126.751 grams. And if you carry out a chemical process which allows you to abstract the iron away from this compound and measure the mass, you find out that the mass ends up being 55.845 grams of iron. And at that point, either you have a chemical means of collecting the chlorine, or you simply subtract the mass of iron, pure iron, away from the mass of the compound to tell you how much chlorine ought to be there, right? So 55.845 grams plus 70.906 grams is equal to 126.751 grams. But more importantly, if you take the ratio of the mass of iron to the mass of chlorine, simply divide 55.845 by 70.906, you'll find out that the ratio is 0.7876. And if you're dealing with the same compound and look at different masses, something rather interesting happens, right? You could go and deal with only 17.754 grams of the compound. Look at the mass of iron, that will be 7.822 grams. Same idea with the 1.995 grams of iron. Out of that, you can get 0.879 grams of iron. If you subtract both of those masses from the mass of the initial compound, this will give you the mass of the chlorine. And if you take the ratio 7.822 grams divided by 9.932 grams, or 0.879 grams divided by 1.116 grams, you find out that the ratio is exactly the same. And so what this tells you, what the law of definite proportion tells you, is that it doesn't matter what amount of compound you're dealing with, the ratio of the masses of the elements present in your compound will remain constant. And in a way of speaking, this is the means by which you can prove that you are dealing with this specific compound, because that compound will have that particular ratio. Now, in terms of like what I mean by chemically abstracting the iron from the iron chloride, I'm talking about a chemical means of separating it. If you have a solution of iron 2 chloride, your green solution right here, right? You take that green complex, dissolve in water, you have your green solution. If you add something like aluminum, in this case aluminum wire to it, a reaction will ensue in which the iron gets reduced and turned into solid iron, and the aluminum, gets changed in the process to forms aluminum chloride, which is a colorless substance for the most part. But the point is that you're gonna get iron solid out of this thing, and at that point you can just filter the iron solid and collect it, dry it and collect it, and then measure the mass. And that's how you technically will get the masses of this thing. So from this 1.995 grams of iron 2 chloride that you dissolved in water, you added aluminum, you isolated the iron from it, collected it, dried it, find out the mass to be 0.879 grams. And at that point, to get the mass of the chloride, all you do is you subtract the 0.879 from the 1.995 grams to get the mass of the chloride, right? Which in this case is 1.16. And so that's how the values that you see here on the table can be gathered and obtained. All right, now the law of multiple proportions is very similar to that of definite proportions, except that now you're dealing with an element that could, or actually a compound that could have the elements present in different ratios, different amounts. So for instance, sticking with iron and chloride, on the one hand, you could have a compound that has only 2 chlorines in it, or you could have a compound that has 3 chlorines in it. And just by looking at the color alone, you could tell that that is a big difference for the compound. We're dealing with a different look for the compound, and in this case, the color just kind of gives it away that they're both different. But the physical properties, the chemical properties, could also be changed. So let's say that the compound didn't have color, so you couldn't necessarily say for sure, which one it was. The way in which you would distinguish one from the other is by looking at the masses once again. Right, so now concentrating on these two original masses, 17.754 grams and 1.995 grams. If you start with that mass for both of these compounds and go ahead and via chemical means, basically add your aluminum wire to the solution containing either of these two compounds, and isolate the iron from them, you'll find out the following masses for both of them. And notice that for the compound with the 3 chlorines, you actually end up obtaining less mass of iron than you did for the previous compound. And that's because now the mass, the 17.754 or the 1.995 grams, there's going to have to be more mass allocated to the chlorine since you have more chlorines. So when you subtract the mass of iron from the iron chloride compound, you find out the mass of chlorine, and taking the ratio of iron mass over chloride mass gives us the 0.776 ratio for iron 2 chloride. But for the iron 3 chloride, we find out that the ratio is 0.5251, and those numbers are distinctly different from each other, that you can certainly say at this point that yes, you are dealing with iron and 3 chlorides if the ratio is 0.5251, or you're dealing with an iron with 2 chlorides if the ratio is 0.7876. And it doesn't matter what amount you start with for the compound, the ratio of the individual masses of the elements will remain constant for the specific composition. So this is the means by which you can tell which compound you have. But right here you have different ratios, right? So now the combination of two elements could lead to different combinations, and that's the law of multiple proportions. All right, now let's talk about Dalton's principles. Dalton was a scientist back in the 1600s, and maybe a little bit more than that, maybe 1700s. But yeah, Dalton actually had some big contributions. In fact, in the realm of biology, the molecular mass of proteins actually get used and defined in terms of the Dalton. Instead of using the gram unit, Dalton is the proper or most used unit for depicting mass of like biomolecules. It's kind of in honor of him. And then you also have journal articles, some of them that have bear his name, like Dalton Transactions. Uh, but pretty much what Dalton, one of the big things that we talk about in intro chemistry that Dalton contributed is a list of rules or conclusions based on observations. The first one being that elements are made of indivisible parts. That means that if you take any one element, doesn't matter which one, you cannot break the element any further. And that would be as far as it goes in terms of keeping the chemical composition intact. All atoms of the same element have the same mass, meaning that if you take a batch of carbon from one source and a batch of carbon from a different source, they will have the same mass. Compounds are made of atoms of different elements, meaning that if you combine, let's say, nitrogen with oxygen, now you have a compound. If you combine carbon with chlorine, now you have a compound. If you combine nitrogen with nitrogen, well, that is not necessarily a compound. We'll get to that in future lectures. All right, now chemical reactions are simply stated the reorganization of these elements or atoms. You don't change the mass going from left to right in the equation, but you do shuffle the atoms and reorganize them, creating new molecules in the process. And the last thing that Dalton says is that atoms cannot be created or destroyed, which is in essence a corollary of the conservation of mass. You do not destroy atoms, you do not create them. Now, I'll have you know that 3 out of these 5 statements is not technically correct, or they are not technically correct. Elements are actually made out of smaller parts. Now, mind you, once you break down the element into the individual parts, you lose the chemical property of that element. But elements are actually made out of smaller elementary particles. We know that from physics. The fact that the observation that all atoms of the same element have the same mass, that's actually not true. We're going to talk towards the end of this lecture about something known as isotopes, which shows you that actually elements are the composition of many other versions of the same element. And the last one, that atoms cannot be created or destroyed, technically is not correct, because nuclear chemistry actually shows us that those 3 points are not entirely true. You do need to deal with specific setups and specific atoms to kind of bypass what these rules say. But in a simple way of thinking, with the type of chemicals and the type of substances that we encounter in introductory chemistry, the 5 statements given by Dalton are actually fairly accurate. The 3 that I highlighted in red, if you want to be technical, are not actually correct. But for the things that we handle, the things that we study in this class, those statements hold true, at least within the scope of what we're going to learn in this class. Alright, so in the next video, I'm going to delve deeper into the history of the atom. We'll talk about the periodic table, we'll talk about the elementary particles that make up elements, and the actual set of events that gets us into understanding what is the atom and where the periodic table comes from. So see you in the next video.